Hello again. Okay, we're back for chapter 4. This is going to be page 101. Actually, I'm not going to be going through all these questions. I want you to do that. What I did is I looked over the questions. I did some myself, and the first couple are don't even you don't even need me to tell you how to do them because you do them all the time. Um, but some of them, especially on page 101, uh, require some explanation. Okay, so anyway, let's take a look on. We'll take a look at page 100. Tell you what, let's do a couple on there. There's plenty to work with. So on page 100, the question is on a standard 6 foot folding rule. Now, my guess is none of you work with a 6 foot folding rule. I did when I was an apprentice. I didn't like it. Uh, I didn't like working with it. And if you do work with one, I think it's a Lufkin, has like a brass slide on the first section that you can slide sideways to, like if you need an inside measurement. It was good for that. I'll give it the 6 foot rule that much. The problem is if you have anything that exceeds 6 feet in length, you're up the creek because the ruler is just so short. And it's nice to have that 25-foot tape that probably is what most of you are working with. In any case, uh, what they're asking is on a 6 foot rule, uh, beginning at 1 and ending at 72 inches, 6 feet. Um, Give the equivalent inch dimensions for. And this one's a gimme, but let me just do one of them. Let's do letter C. 3 feet equals 36 inches. Okay, I think you can all handle that. All right, so that's the end of number 1. You all know how to do it. You can fill in the rest. Now, one thing I did mention, I added it to the right on the side of that question, my own information for you. It's technically not plumbing, but it's something you all should be well aware of. If there's anybody here who's a kind of a rookie in the trade, and you've noticed you got the 16, 32, 48, 64, 80, and so on, and those numbers are in red, the only ones, not the foot, not the 12, the 24, and so on, the 16, the 32, 48, they're in red. Okay, those are for carpenters. That's where they're going to be putting their floor joists most of the time, probably 90 some percent of the time. Their floor joists are 16 inches on center, which means they're 16 inches apart. The clear space between them, and a lot of you guys know this because you do this all the time, is 14 and a half inches. All right, so that's how much space you have to get your drill up there, put the drill hole through to get the pipe up, and so on. So I'd make a note of that. To me, that's really important. Be aware of um, those marks. Okay, number 2, convert the following dimensions in feet and inches to their equivalent in inches. All right, let's do letter C again. 4 feet 6 inches. It looks like 54 inches. Okay, so it's just 48 inches, 4 feet, and then just add what's left. Okay, it comes up to 6. All right, I think you all know how to do that. Okay, number 3. Convert the following dimensions given in inches to their equivalent in feet and inches. Okay, so now they're giving you the reverse. Now we're going to give you, let's do that again, letter C. All right, let me just put this time down here. 3. Okay, letter C again. Okay, it just happens to be 54 inches, which we just had in the last problem, but it's 54 and a half inches. So how many feet would that be? All right, just divide 12 into that, and you come up with 4 feet, 6 inches, and actually 6.5 inches. All right, so letter C would be 4 feet, 6.5 inches. Again, you guys work with these rulers, these tapes every day, so I hope that this is not a mystery to anybody. Okay, now this, we're moving. We're going back into 4th or 5th grade here. Question number 4. Well, you're going to see this out in the trade? Possibly, but most likely not. Where you add up numbers, fractions, where you don't have the same common denominator. Common denominator is that letter on the bottom. I mean, the number on the bottom. So what do they got? Okay, my lighting here is not the best. All right, well, let's do number C again. All right, let's do 4C. They get 10.5 by 1.25. All right, let's see what that looks like. By 1.25. Okay, so we're adding it. All right. Now this one here, I think most of you could do this in your head, and all of you could. But how do we deal with this? Some of them are not quite this easy. All right. First of all, what we're looking for is a common denominator. What number down here will both of these go into? Well, in this case here, of course, the 2 will go into the 4. So that'll be it. So we have, I'll put here equals 10 and something over 4 equals 1 and 1 over 4. That doesn't change. That stays the same. But this one, 2 goes into 4 2 times. 2 times 1 is 2. Okay, now I know some of you haven't done this probably in many years, but that's what it looks like. Okay, so when you add this up, what do you got? 2 and 1, 3 over 4, 11 and 3/4. Okay, if you want to make a note of that, again, if you're very rusty on this math, that was number letter C. Okay, so letter C is 11 and 3/4. Okay, now what happens if the number is going to exceed 1? I'm going to make one up. Okay, I intentionally made it so the fraction can't be added. We're going to have to do one extra step. So let's do this. Let's go over here. Okay, common denominator, same thing. 4. All right, this is the same. Now this one, 2 goes into 4. 2 times 1 is 2. Okay, now I got a problem. This is going to come up to 9 and 5/4. Okay, and we can't have that, right? That's an improper fraction. That's, if you remember when you're a kid, that's when they mark it wrong on you. All right, so what happens? We got to convert this into a whole number. So what do we got? We got 5/4 equals 1 and 1/4, right? Okay, so we add that. All right, and we're going to add it down here, 10. Oops. This goes up to 6, right? Because we had the 1 right here and 1/4, right? And over here we have 1 and, I'm sorry. Let's try that again. I should have done this before you guys came on. All right. Try this one again. Equals 5, and it's going to be a 4, right? I think we're all good with that. And this one's going to be 4 here, 3/4. And this one is going to be 2/4, right? Okay. So what do? We got 9 and 5/4. All right. So what we have to do is take the 5/4 equals 1, right? 4 times 4. 4/4 is 1, and 1/4 left over. Okay, and add it to, so this is going to be 1 here, plus 1 equals 10. Okay, sorry about the follow up there. All right, but I think you all remember that. Basic math. Okay. And then we got subtraction. Same deal. Let's stick with letter C again. Letter C is 12 3/8 minus, no. Let's do letter A. 5A. 10.5 minus 1.5. Do we have to do anything to this one? No, this one's a gimme. All right, so we're just going to deduct it. 10 minus 1 is, you just do it right here. 9. 1 less 1. 1/2 less 1/2 is nothing. So the answer is 9. Okay? That was a gift. All right, now, they're not always quite so easy, so let's try another one. That was the first one. That was letter A. Okay, letter B. Actually, B is a good one. 8 3/4 less 1.5. Okay. Again, we can't work with this because the common denominator is different. So, what goes into both of them? What will they both go into? It's going to be 4. So we have 8 and 6/8, right? We have 1, and actually this would be a 4 here. 2 goes into there too. There it is. And I know I did that. Okay, don't pay attention to that. All right, that's correct, like that. Had something else in mind. But this is a minus. So 8 less 1 is 7. 3 less 2 is 1. Done. Okay? Very simple. Unfortunately, it's not always quite that simple, but that's a good sample. All right, that was number 2, letter B on number 5. Now I'm waiting for them where they're going to spring, where we have to borrow something. I think it's going to be the next one. It is. Okay. So let's get rid of this. Let's go to letter C. Letter C is 12 3/8 minus 3/4. Okay, so what do we do? Common denominator again. Okay, so we get 12 and 3/8 minus 3/4. Okay, so this is going to be an 8. 4 goes into 8 twice, times 3 is 6. There's the 6/8. All right, we can't do that. Obviously, you can't deduct 6 from 3. So what we're going to do is borrow 1 from the 12. I'm sure this is starting to sound familiar. So we'll go over here, right? And we're going to take 1 away from here, like that, and make it 11, right? And that's going to be 11, which means we're going to have 8/8, right? 8/8 equals 1. Okay, so we stole 1 away from here, made that 11. So we got 8 and 3 is 11 over 8, like that. Okay? All right, but that's what we did. We crossed that 12 out, took 1 away, and added 1 up there. Excuse me. Okay, next, we got a 6/8 just comes back over here. And what we have? Now we can deal with it. All right, so we have 11, and 11 less 6 is 5. 5/8, right? Okay, 11 less 6 is 5. That's it. Okay, so that's all I'm going to do on that basic math. Okay, we went back to probably early middle school for that, and a little refresher. Okay, I also mentioned that Pythagorean theorem in the last class. That was where you take 3 sides of a triangle. Okay, you got a triangle. It's 3 inches by 4 inches like that. This is the one they always use as a sample. Remember, if this is letter A, and this one is C, remember this, A squared plus B squared equals C squared. All right, so what do we got here? 3 inches, 3 squared plus B. All right, that was just simple math. 9 plus 16 equals C squared. This is 25 equals C squared. Square root of 25, which is what this is. So C equals 5. It really is not hard. It sounds like a big deal. You hear that Pythagorean theorem, something from the Greeks, I guess. Not a big deal. Okay. Now, what I did on my own today, which I had never done before, I took a different triangle, like looks like a pyramid, like this, and it's the same thing. You call this. Hold on. If these are the same, we'll say that this is 6 and 6. All right. If you square both of these, add them up, the square root would be this. All right. It does work out. So remember that. This is the best formula to remember, the best problem right here. It's the easiest one. Make a note of that. Okay. So let's leave those away alone. And I'm going to go to tank volume. I don't know that we've done this. I think we have, but in case we didn't. Now what I'm doing is like running kind of alongside of what the book is covering, just so you have a little practice with some of these formulas. All right, this would be like a rectangular kind of tank. So just a tank that was like square dimensions or a rectangle. All right, and the formula would be the length times the width times the height, right? That would give you the dimensions in, if you were doing it in feet, it'd be cubic feet, right? Makeup air, we did that in the basement, remember? Makeup air for a fan in a can. This is exactly what we did. Length of the house, the depth, well, the width, and then the height of the ceiling. And we added that up, 10,000 square feet. That's how much air we had for the boiler. If the boiler needed more air, the boiler plus the water heater, then if they didn't come up to enough, if we came up short, we had to add the fan in the can. So what we're doing is we're doing the measurements now for a water tank, right? This is something rather than just the capacity for air, like the basement. This would be some kind of tank. All right. So let's work one out. I actually don't have a sample here, but we can do one pretty quick. I think they call it cubic contents. I believe that's one name they call a problem like this. Equals length times width times height. All right. Let's say the length is. Let's do that. Let's do the seller again. Give you a little practice on, because the one for figuring out for water. You're not going to use this one. All right. They mention it in the book here. It's not happening. You're not going to be designing tanks, but you definitely will be figuring. Just every heat job you do, or you got a boiler in the basement, you should be doing this. So let's do that one again. I'm going to give you the dimensions for basement, right? And we'll figure out how many cubic feet of air is in the basement. Whether it's air or water, it doesn't matter. We'll convert it to water. Okay, so the basement is 40 feet long by 26 by 9 feet high, right? That would take you right up to the subfloor, right? Up between the floor joists, 9 feet. So, what does that look like? Well, years ago, we didn't have these calculators. By the way, let me give you a little history lesson. My younger brother, who retired actually just a month ago, he's a college professor. He's 71. Back in 1974, he had one, and it looked something like this, very much like this, and it had a few engineering functions on it. And in 1974, that calculator was worth $300 in 1974 dollars, which today would be about maybe 1,500, at least 1,500 by today's dollars. And it was only about this big, but it was such a big deal, right? It was a very big deal. Now, $5, if that. Okay. Plus, I don't think there was solar back then. In any case, let's see what we got. We got 40 times 26 times 9 equals 9,360. Remember now, this is in cubic feet. Now, if you remember, I'm not going to go, I'm going to figure it all out, but if you got a boiler and you take the input of the boiler, right, and you take the input on the water heater, and you don't have enough, that's when it's fan in the can time. But in this case here, let's see what we got. All right, now I've got cubic feet. The problem in the book is talking about gallons. Now, right away, I'm up to a big swimming pool. If this is going to be water, this would be a pretty big swimming pool and also rather deep. Okay, so let's think swimming pool. 1 cubic foot, we got to figure this out. 1 cubic foot equals, remember this, 7.5 gallons. And nothing to do with weight. We're not doing weight. Just looking for volume. Okay? So, what do we do with this? We take this times 7.5. Okay? And get rid of this. Okay? A lot of gallons. A lot of gallons. If you got a pool that big, I don't know what you're going to fill it with. You get those trucks that come out. What are they, 8,000 gallon water trucks? You have a lot of trucks to fill up a tank that's a pool that big. Oh, this is bigger than this would be. This probably would be too big for a residential pool. I mean, with that kind of depth, you're probably looking at a pool that would be actually twice that the dimensions. But in any case, this problem here, the way I did it, 40 feet, 26, 9, Here's the 7.5. Don't forget that. There's the gallons. How much does that water weigh? Let's say you're an engineer and they're going to put a water tank on the top of a skyscraper, which some of them have. You might have seen some horror movies where, not horror movies, but like fire movies where they blow the tank on the roof and the water, which is feeds from above down with a pump, pumping water up into the tank all the time. So they got to calculate this kind of weight on top of the building. So what's the weight of this many gallons? Okay, now remember, 1 gallon, right, equals 8.33 pounds. Remember that? 8.33 pounds. By the way, that's 7.5. You might see it. I believe it's 7.48 is more accurate, but that's close enough. Okay, so if we have 7,200 times 8.33, okay, you got 584,766 pounds. Pretty heavy. Okay, pretty heavy. All right. So that was another problem that they talk about. They're doing. Oh, the book also. They do something a little tricky here. They do this, and then they say, "What about if it's only 6 inches deep?" Okay, if the height is 6 inches, a foot would be one right here, right? So what would 6 inches be? Be half a foot, right? Or 50%. So it'll look like that. Okay, so if they want something that's only 6 inches deep, now this is a tricky one because they'll throw this out there for like a roof, and we'll say there's a parapet, I think they call it, all the way around it. You know, the water can go 6 inches deep before it floods over. How much would it weigh? Or, you know, what they're trying to do is get a little sneaky over here. Okay, in this case, the book did look, there's a problem. I think it was, I mentioned it here, 6 inches deep or half a foot deep. All right, let's see what this would be. How many gallons? We'll just do gallons. This is only 6 inches like this here, right? We'll say it's a roof, and it's designed to hold up to 6 inches of water before it spills over. How many gallons is that going to hold? All right, so it's 40 times 26 times 0.5 equals 520. All right, that's roughly 1,000 and change, times half of that 1,000 would be 500. Yeah, 520 equals 520 cubic feet. And if you want to do the weight, just multiply that times 8.33, be about 40. What? All right, I said I wasn't going to do gallons, but since I already got that file, let's carry it on. 8.33 equals, pretty heavy. And let me try that again. 520 times. There we go. Okay, so that's how much it would weigh. So if you had a roof, really just about the size of a house, and it was dead flat, and it could hold up, you know, the water, you know, those little sides on it all the way around. There's an awful lot of weight on that roof. Okay, that's it for tank volume. Now, I don't think I'm going to have enough time. I'm sure you're going to miss this. uh, to do cylinders. I'll just mention to you the cylinder formulas are on the formula sheets I gave you early in the semester, right? Those 3 pages. There's 3 formulas we're going to work with. And I just don't have time to do formulas right now. I've only got about 5 minutes left, 6 minutes left. So I'm going to skip that. But cylindrical capacity, we'll do on another night. All right, I'm going to make a note that I skipped that one. Okay, now one thing I do want to cover, it won't take that long, is a 45-degree offset. Now this one, occasionally you do. Now I heard of a guy that actually used this formula. I mean, he's actually my teacher, my night school teacher. Right, I didn't have him day school, but I worked with him in day school. But he was my night school teacher before I worked with him once I became a teacher. And I was told that he actually used these formulas. So let's say that you're doing this. You're going along and you did a 45-degree offset like this, right? I'm only going to work with 45 degrees. And we'll say that from here to here was 10 inches, like that. Okay? What is this? Okay, now, this one you absolutely have to know. Even if you don't use it in real life, doesn't matter. You got to know how to do it. Now, the book calls this here the run. And the offset, right, is this right here. Right, from here to here. So the run goes like that. In carpentry, I think they call it the rise, like if you're doing a flight of stairs, the run and then the rise. But for us, we don't say that. Now the question mark is the one they call the travel. Okay, get used to that because we don't use that name. At least I never did. All right, we call that the offset. The offset really is this right here. So how long is the offset piece, which is called the travel? All right, there's a formula you need to memorize. All right, the travel equals the offset times 1.414. Okay, it's one of those constant things like pi, like 3.14. Okay, so if you travel, if your offset is 10, that's the offset right here. You're looking for travel, You multiply 10 times 1.414. Okay? Travel equals 10 times 1.414. You can all do this. Just move the decimal. So it's 14.4141. Okay? So this here is 14.41. Now, obviously, that's the absolute easiest sample you could ever get. And I believe the book even the book does use that on page 94 when they're explaining it. They even show you a couple of fittings. Now, just a caution. Don't plan on when you take the test, don't plan on a chart for this. You better know the 45 degree, the 4.414. Now, on page 94, they call it a table of tangent ratios. Okay, you'll see that we're not going to be using those 1-to-1. No, that's not the one I wanted. I'm sorry. Forget that. Okay, don't pay any attention to that. But the offset here, the 10-inch offset, and the travel on a 45 degree. Remember that. That's the key here. 45 degrees. Right? You're working with 45s, which is the usual. That's what it is. Now, if you're working with 22 and a halves or 60s, of course, this is a different number, the 1.414, which I really don't have right here. But the 45 is probably the one that you're going to be asked about. And there it is. Okay, so take that sample, put it aside. Okay, just a couple more things. We're just about on time. Okay, they mentioned meters and inches. Okay, here's the good news. Since I was a kid growing up, the foreign cars, this is like back in the late 50s, early 60s, mid 60s, foreign cars were usually metric, right? And I'm sure you guys know mechanics, and they have two sets of wrenches, right? They got the metric and they got the S8, they got the inch ones. Real pain in the butt. We got lucked out. Our trade has, for the most part, stayed clear of metric measurements. Occasionally there's a metric number here and there, but for the most part, we're lucky. We're very lucky. Ask your buddies with the car mechanics. Now, I don't know that the American cars ever switched over to the metric. I don't think so. But again, I'm not a mechanic. So that was my dealing with it. Now, the metric actually does go back pretty far. Like if anybody here has any knowledge, like of World War II, for example, they had a lot of the guns were in millimeters, and they still are. 81 millimeter mortar, 105 howitzer, all these numbers, they're always in millimeters, even back in the 40s. And when I was in the service, the tanks we were using, it was a little over 50 years ago, were 105 main gun, which was 4 inches. So a very rough relationship. 25 millimeters is roughly 1 inch, because I remember 105 millimeters was just over 4 inches. In fact, I did the math out a little while ago. It does work out. And the formula, I'll just give you one. 1 inch, to convert it to millimeters, you multiply it by 25.4. So you got 4 inches, like that gun I told you about. You multiply 4 times 25.4, you come up with 101.6. Now, if you jump that up to about 4.1, that's about right. Like I said, it's a little over 4 inches is 105. So you can read that. Don't get too excited about that conversion between millimeters and inches. I don't know that that's been popping up on tests. This book, remember, is from Ohio. But there are some charts. Check it out. And there is some questions. More important one is slope. This will be the last thing I cover. The slope to piece of pipe. For example, let's say that you had 76 feet and you're going to run it at 1/4 inch. Now, my brother, he did start out, he did have his plumbing license in was it Colorado before he went back to school, became an architect. And he got pretty good. He was building houses and they would shot a lot of grades, he and the guy that he worked with. And he just got done running 100, roughly 80 feet of pipe, and he only had 1/8 inch pitch. And I know he'd probably rather put more on it. But occasionally you might be running pipe like that, but most likely you're not. But however, that doesn't mean anything. The code just might, the plumbing code, our plumbing code might be asking a question about that. Let's say you had, let's try 76 feet, 1/4 inch pitch to the foot. So we got 1/4, right, times, let's say let's try an easy one. Let's say 10 feet. Let's see how this is going to work out. 10 over 1. So quarter inch to the foot, that would be what? 10 feet? How many inches is that? Looks like about 2.5 inches, right? Every 4 feet is an inch. Now you guys have all put up hangers on new houses. You go every third floor joist, right? Put up a hanger. The next one, depending on which way you're going. If you're pitching up, you deduct one. So you just keep on going, nice and uniform, right? So every 4 feet is an inch. So 10 feet would be 2.5 inches. So let's see how that works out. So we got 10 over 4. This would be 4 goes in 2, and 2/4 equals 2.5. Okay, so there's a simple version of how you find out what the pitch will be for a long distance. Now, if you're going across the whole cellar, some of you guys I'm sure have done that. You might be going like 4 or 5 inches, right? But like you got to clear a doorway. Here's another one. You got to clear a doorway. I've run into this before. A window or doorway or something. Can I sneak over that whatever's down at that end? I don't want to get down there and find out I did all this 20 feet of pipe for nothing. So you have to figure it out. So occasionally this pops up. So let's do 76 feet underground. 76 divided by 4 equals 1, 3 left over, 19 inches of pitch. So if I had to run 76 feet, big building, small commercial, big house, I would be dropping 19 inches. That's a lot. 19 inches probably means you're not going to clear a door frame. Now, how do you get around that? Remember, 4-inch pipe, you can go 1/8 to the foot, right? Which is half of this. So divide that by 2 equals what? 9.5. This would be 1/4 inch right here. And this would be 1/8 inch, right? Right there. Okay, now I have used this myself a few times, and maybe some of you guys have. It's nice to know so you can get out of a jam, right? 4 inches is nice because it's flexible. You can go either way. Normally, I know you go for a 1/4 inch, but if you're in a jam, you can go 1/8 inch. Also, if the septic tank appears higher than they promised you it wouldn't, before you panic, don't remember you can change your pitch legally to just 1/8 inch to the foot. Okay, I think that's it. Definitely got a full class, and I will see you next week.